In this video, we are going to start Lesson 1 from Part 1 inside of Unit 5 for College Algebra. The first part of this unit will cover polynomial functions, and the second part of this unit will cover rational functions. Now, hopefully these types of equations and functions are familiar to you. Our objective in these units, or this unit, is to learn a little bit more about each of these functions and their behaviors, as well as applications of each. So let's start off by reminding ourselves a polynomial function is the sum and or difference of several terms that are made up of coefficients, variables, and exponents. So each term contains a coefficient, a variable, and an exponent. The terms within a polynomial typically contain one variable and must have real number coefficients and non-negative integer exponents. Non-negative integers are also known as whole numbers, so therefore our exponents must be whole numbers. So I've also included these notes here. This double bar R and double bar Z represent the list or set of real numbers and set of integers respectively. By putting a little plus symbol after here indicates that we're talking about positive or non-negative integers. So if I were to list non-negative integers or whole numbers, that list would start at 0 and continue upward indefinitely. So if I'm trying to list the set of positive integers or non-negative integers, this would be the set. So when we're talking about exponents, they must be within this list of numbers. We're not allowed to use fractions, we're not allowed to use decimals. We avoid those for polynomials. And so now the question becomes, in this list of 6 functions, they're all functions, but of this list of 6, which one of these are polynomials and which ones are not? If they are not polynomials, please explain why. If they are polynomials, state the degree, and I'll see if you remember what that is. Go ahead and pause the video and resume playback in a moment to check your work. So I would say that A is, yes, a polynomial. We have terms that are separated by addition or subtraction signs, and within each term we have a variable, coefficient, and exponent. Now this first term is written just as the number 2, but let's remember that the number 2 could technically be written as 2 times x to the 0th power, or to the power of 0. And x to the power of 0 is 1. 1 times 2 is still 2. So this is just another way to write the number 2. And now we can clearly see a coefficient, a variable, and an exponent. The exponent is a whole number, and the coefficient is real. And that's the case for both of these. Now as far as our degree goes, maybe you recall this, maybe not. The degree is simply the largest exponent within the polynomial. And we'll talk more about why we focus on the degree a little bit later. And so that's why we would say the degree is 4. For B, we're saying that this is not a polynomial, because if we were to write the square root of x with an exponent, that would be x to the 1/2 power, and that violates our rule that we must have positive or non-negative integer exponents. This is a non-integer, so therefore we are not dealing with a polynomial. Similarly, in equation H, while the numerator is a polynomial and the denominator is a polynomial, we would think of this as, or we could think of it this way, as the quantity x squared minus 2 times x cubed minus 1, but that group x cubed minus 1, since it's in the denominator, contains a negative exponent of negative 1. Now in the matter of simplifying this, we could, of course, write it as a fraction, but I've written it this way because we see now that we have a non-negative, we have a negative. It's not a non-negative integer within the expression. So that's no good for our polynomials. Now question D is kind of interesting. We have the number 0, and similar to any other constant, we could imagine that there is a coefficient. We can imagine that 0 is the coefficient, some letter is our variable, and then we might have an exponent. The interesting thing, though, is it doesn't matter what the exponent is as long as it's non-negative, and of course it would be in this case a non-negative integer. I should say it could be a non-negative integer. It could be anything else, because this 0 times whatever the result of this exponent is will still be 0. However, even though this exponent could potentially be not an integer, or it could be a negative integer, and 0 times whatever this result would still remain 0, we do consider the number 0 a polynomial. In fact, we call it the 0 polynomial. And the 0 polynomial does not have a degree. The degree is undefined. So again, 0 is essentially a constant, and because of its special nature, for the potential of there being a power that doesn't follow our criteria, we consider this a 0 polynomial, and we would say that the degree is undefined. For part E, again, this is a polynomial. Imagine that we had x to the power of 0. Well, x to the power of 0 is equal to the number 1. 1 times 8 is still 8. So if we were to add on x to the power of 0, we would still have the same value, 8. Therefore, 8 is considered a polynomial. We call that a constant polynomial, and its degree is 0. For h, we do have a polynomial, and because of the multiplication, it may not be clear that it is a polynomial or that we have a specific degree. But imagine if we simplified this by combining like terms and eliminating parentheses. We could expand x minus 1 squared to be this, and then multiply those two together. That would complete the exponent step in our order of operations. Then, moving on to multiplication, we can distribute this leading coefficient. And clearly now we have a collection of terms. Each term contains a coefficient, a variable, and an exponent. The exponents are all whole numbers, the coefficients are all real numbers, and each of these terms are separated by an addition or subtraction sign. So clearly we do have a polynomial, even though it's written in a slightly different form originally. And now we can clearly see that the degree of this polynomial, the largest exponent, is actually 5, not just 3. Now what's interesting and particularly helpful, as we'll see a little bit later, is that the product of this exponent and this exponent, should say the sum of the exponents, but the result of the product process will indicate our degree. So that'll be helpful as we talk about multiplicity here moving forward. So moving on for some more basic information, this time with regards to the graph of polynomials. All polynomial graphs must be smooth and continuous. There can't be any jumps or breaks in the graph of a polynomial, and there can't be any sharp corners in a polynomial. A lot of times we'll see that develop as a result of absolute value functions or perhaps piecewise definitions, but a polynomial itself, its graph must be smooth and continuous in its entirety. So therefore we would state, or we would note that the polynomial's domain, any polynomial domain, is all real numbers. And this really speaks to this idea of continuity, but what we're saying is that any real number value can be substituted in for x, or into our independent variable of a polynomial, and we will be able to compute or calculate a real number result. There's no number that we would plug into a polynomial that can't produce a real number result. So with that commentary in place, or conversation in place, what do you think about this question? Is the graph in this figure, figure number 6, the graph of a polynomial? And I would say yes, because the graph does appear to be smooth and continuous. The arrows at either end imply that the graph continues essentially in this direction forever and ever. And there doesn't appear to be a break anywhere along the graph, and there are no sharp corners. This is kind of interesting right here, but we're not meeting at a corner and then turning away, but it's actually a smooth transition where we sort of bump into this x-axis and then curve back away. That's kind of a smooth transition. So yes, because it is smooth and continuous, I would argue this would be a picture of a polynomial. Based on the graph, could you estimate or guess what the degree might be? Well, this answer requires some prior knowledge, and the answer I would go with is 5. We would say that this is probably a degree of 5, and that's because there are 4 turns or direction changes in this graph. I don't like using directional changes as a description because that's not always the case, but turns I think are a little bit better. This graph, if this was, say, a map that you were driving a car on, let's say we were traveling from left to right, if in order to make it around this curve in the road, we have to turn our steering wheel to the right. So I'm going to count that as 1 turn. As we continue to move, I'm going to have to turn my steering wheel back to the left to make it around this curve, so I'm going to call that curve or turn number 2. Here we have turn number 3 and turn number 4. Now, the rule of thumb states that the degree of a polynomial is 1 greater than the number of turns. Now, that's not always the case. The degree could be larger than that, but it can never be smaller. So, if I'm saying that the degree here is 5, then I'm suggesting that the polynomial has the largest exponent of 5, and there's most likely an x to the 5th power plus some additional information, and there might be a coefficient in front of that as well. It would take some further analysis to describe what the rest of the polynomial might be. Now, how many zeros are found in this polynomial? Well, to answer that, it might be helpful to note that zeros is another name for roots. It's another name for solutions. And it's another name for x-intercepts. So zeros, roots, solutions, x-intercepts, those phrases are all synonymous. And in this case, we see an x-intercept here, 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 and here. So I would say that there are 4 roots, or 4 zeros. Now, if this graph had been shaped just a little bit differently, we can still maintain the same number of turns, but have an additional 0 to it. So if this turn had not occurred down here right against the x-axis, but instead went above the x-axis and then turned down below, well, then that would produce an extra 0, and we would end up with 5. But as it turns out, that would be the maximum if our degree is indeed 5. So it's worth noting here, if this is a 5th degree polynomial, there would be, therefore, a maximum of 5 zeros. There could not be any more zeros than the degree of the polynomial. So I kind of jumped ahead here and answered this next question. What's another name for the zeros of a polynomial? Well, a lot of times you'll hear the word roots. That's probably the most common phrase that's used in place of zeros, but also solutions and x-intercepts. Those are other names for zeros of a polynomial as well. And so if we're told that another name for zeros are solutions or x-intercepts or roots, let's suppose that we know that the behavior of some particular phenomenon must follow some sort of polynomial graph or polynomial equation. And we know that this polynomial is a degree of 3, and the zeros or solutions occur at -3, 2, and 5. Could we find the rest of the polynomial and therefore interpret additional information about it with the equation? And I would answer yes, we can do that, because in order for a polynomial to contain a solution at x equals -3, and maybe I'll show this up here, in order for a solution to occur at -3, we could essentially create a binomial factor of our polynomial by moving this -3 from the right side to the left. We do that by adding on both sides. We now have x plus 3 is equal to 0. And by the way, here's where the name 0 comes from, because the binomial factor associated with the polynomial is indeed equal to 0. So I'm going to make this as one of my factors of the polynomial. There's another solution at +2, and when x is equal to 2, then the factor x minus 2 will equal 0, and it must be a component of our polynomial. Excuse me. And lastly, if there's a solution at 5, then the factor x minus 5 must be a component within the polynomial, and its factor would be equal to 0. So here's a polynomial that does have the zeros located at -3, 2, and 5. And after I FOIL this back together, you'll notice that its degree is 3. So in fact, I'd like for you to do that right now. You'll have to FOIL these first two terms and then distribute the x minus 5 in. You may not have enough room on your handout right here, but perhaps off to the side or on another sheet of paper, you can complete this exercise. Pause the video now and resume playback in a moment to check your work. And so I would argue that your end result for this polynomial is equal to x cubed minus 4x squared minus 11x plus 30. And I obtained that by first FOILing these first two binomial products into this result, x squared plus x minus 6. And then distributing this last binomial into the product of the first two binomials. We had to do that with two sets of distributions to obtain these components. And then when we combine our like terms, x squared minus 5x squared produced our negative 4x squared, and negative 6x minus 5x produced negative 11x. Along with x cubed and 30, we ended up with this particular polynomial. Now, the second part of our instruction said to use a graphing utility to graph the polynomial and verify your result. And I'll leave that as an exercise for you to complete, but what we should be on the lookout for, of course, is a polynomial whose graph touches the x-axis or strikes the x-axis at -3, +2, and +5, because those are solutions or zeros, and has at most 2 turns, because the number of turns or curves has to be 1 less than the degree. Now, I know a little bit more about polynomials, and hopefully you do as well. And if our leading coefficient is positive with an odd degree, I know this right side tail has to point up and this left side tail has to point down. And in order to connect these 3 data points with a curve or a continuous line, I think this would be a general shape that we're on the lookout for. So the graph on your graphing utility, either Desmos or your TI Inspire, should have the same characteristics of this quick sketch. And so now I'm going to pull some information together from what we've discussed today and hopefully what you recall from your discussions in the past. And let's see if we can sketch a picture of this polynomial as it's written in factored form by locating the zeros within each of these factors and accounting for this notion of multiplicity. We'll talk a little bit more about that. So let's start with this. First off, the 0 can easily be identified in factored form because the name 0, as we stated a second ago, indicates the x-intercept occurs when these factors are set equal to 0. So when x minus 2 is set equal to 0, we know that we have a solution or an x-intercept at +2. When x plus 3 is set equal to 0, we know that we have a solution or an x-intercept at -3. And we also know that when x minus 1/2 is set equal to 0, we end up with a solution or an x-intercept at +1/2. Before we start sketching, I would like to consider polynomial end behavior. And this is something that's usually discussed in an Algebra 2 class and a pre-calculus class, and I know many of you have had those classes before this one. So I'll remind you of the following chart or combinations that might exist when describing the tails or the end behavior of a polynomial. So what I'm going to do first is I'm going to build a chart, and on the left-hand side I'll indicate the leading coefficient, because the leading coefficient affects the tails of our graph. Our leading coefficient can be either positive or negative, and that'll have an effect on the behavior of the graph. And in addition to looking at the leading coefficient, I'm going to look at the degree of the polynomial, and the degree can either be even or odd. and that will affect the shape and behavior of the graph. If our polynomial has a positive leading coefficient and an even degree, then the tails, or the ends of the polynomial, will both be pointing upward. If our leading coefficient is positive, but our polynomial has an odd degree, then the right side tail is pointing up while the left side tail is pointing down. They point in the opposite direction. With an even degree but a negative leading coefficient, both tails point in the same direction, but both are pointing down. And with an odd degree but a negative leading coefficient, then the right side tail is down and the left side tail is up. The number of turns and additional behavior in between the tails is also determined by the degree and the remaining terms of the polynomial, which would require some additional investigation. But at least this we know is true by simply looking at the leading term, the leading coefficient. Again, when the degree is odd, the tails point in opposite directions. When the degree is even, the tails point in the same directions. With a positive leading coefficient, the right side tail is always pointing up. With a negative leading coefficient, the right side tail is always pointing down. So if you can memorize this chart, great. If you can memorize the behavior, that's just fine as well. Because again, with an odd degree, the tails point opposite of one another. With an even degree, the tails point in the same direction. And so with those characteristics, I think you'll be able to keep this pretty well straight. Now, in order to obtain the degree or leading coefficient for this polynomial, we don't necessarily have to FOIL all of this together, and that would be pretty difficult to distribute all of these together because there's a pair of double binomials here and 4 binomials here. There's 4 sets, and I really don't think we need to multiply all of this together. X minus 2 and x plus 3 2 times, and x minus a half 4 times in a row. That would just take us a little bit longer than I would prefer. So one option and one pattern that presents itself after doing lots of work with these polynomial functions is that in order to determine our leading coefficient, all we really have to do is focus on the leading coefficient or the leading term from each of these factors. If I were to come through and multiply 5 times x, and so on, what I would end up with is 5x to the 7th power. And through the process of distribution, I would end up with many, many like terms that would combine. And I'm not particularly interested in those right now, but I might be interested in the trailing term at the very end. And as it turns out, we can obtain that by multiplying this 5, because it would distribute in, and then multiplying all of the trailing terms in each of these binomials as well. So 5 times negative 2 times 3 times 3 times negative a half, 4 times in a row, ends up being a negative 5.625. Now, having the leading term and the trailing term is particularly helpful because, as we just described a second ago, the end behavior is determined by our leading term. We have a positive leading coefficient and an odd degree, so I know that this polynomial has to behave like this. Its tails have to behave like this anyway. So odd degree, positive leading coefficient. The right side tail is pointing up, the left side tail is pointing down. What this trailing term, or the constant, tells us is that this is where the graph is going to cross our y-axis. This is our y-intercept. And I know that this is the case because all of the terms that lead up to this point contain an x value. And a y-intercept occurs when x is equal to 0. So if x were set equal to 0 amongst all of these terms, those terms would all equal 0 except for this last one. When x is 0, the y result is negative 5.625, and therefore we have identified our y-intercept. So with a little bit of interpretation and a little bit of math, we can actually predict what the shape of this graph will be without having to rely on completely completely analyzing the function. Because of the factored form, we know that there is a 0 at positive 2, negative 3, and positive 1/2. So I'm going to label the axes this way. Every 2 grid lines is 1 unit on the x-axis. And I'm not going to specify the y-axis because I really don't know the height or the dimension along the vertical axis. But again, we've got a 0 at positive 2. We have a 0 at negative 3. And we have a 0 at positive 1/2. Because of the odd degree, the tails are going to be pointing in the opposite direction, and because of the positive leading coefficient, I know that this right side tail is pointing up. So if the right side tail is pointing up and the other tail has to be pointing in the opposite direction, I know that this one's pointing down. And now I've got to come up with what the behavior of the rest of the graph might be. Because the degree is 7, at most I could have is, the most turns that I could have is 6. I could have 6 turns along the way. So this thing might do something like this. And that sketch has 1, 2, 3, 4 turns, and that would be fine. It could be a little bit more aggressive than that as well, apparently. Now we have 1, 2, 3, 4, 5, 6 turns. But you'll notice that in either case I did not cross the x-axis again. This would be a no-no. This cannot happen because, well, we didn't identify any other 0. There were no other zeros in based on the equation. So this graph cannot exist because, again, there are no more x-intercepts, no more zeros to this function. Now, a note on multiplicity. This is actually going to give us a better idea of the shape of this graph. You'll notice that this factor, x minus 2, technically has an exponent of 1. And so what we would say is that at the 0 associated with this factor, the graph will behave essentially like a linear function. And we learned a little bit, or reviewed a little bit, about linear functions in our last unit. A linear function, of course, is a straight line. So at this intercept, I would imagine that the graph is coming through the x-axis, and if I were able to zoom in exactly on that data point, it would almost look like a straight line coming right through the x-axis. So this much I know is part of the behavior of our graph. At the next 0, at x plus 3, the 0 associated with it, the graph is going to behave like a squared graph, or a quadratic graph, or a parabola. And so over here with the x-intercept at negative 3, if I were to zoom in on this 0, I would expect the graph to behave almost like a quadratic right in that location. Now, it's not going to behave exactly like a quadratic, but what that even degree and that multiplicity of 2 is telling me is that this 0 is a 0 in such a way that the graph bumps into or touches the x-axis, but then turns away immediately, much like a parabola would. Similarly, with the third 0 at positive 1/2, we're going to behave like a quartic graph, or a 4th degree polynomial. Now here again, with a 4th degree polynomial, we can bump into the graph and turn away, and that might happen above, on top of the x-axis, or below. But only one of these would be appropriate in this situation, and hopefully you would recognize that it's the second one that's better here. Because if we're creating a smooth and continuous graph in which all of these intercepts are connected, you'll notice that the graph will never cross the x-axis to bump down into this equation, to bump into that 0 again, because these x-intercepts were not originally identified. However, coming from below can happen in this sketch. And if we graph or connect these points with a smooth and continuous line, this might indicate the behavior of this particular graph. Moreover, we noted earlier that our y-intercept was supposed to be at negative 5.625, and even though we didn't specify the scale, this location right here could potentially be negative 5.625. If the graph somehow did cross the x-axis and approach this position like I originally stated, well, now we're looking at a y-intercept that's a positive value, which can't be the case. So I'm fairly confident in stating that this is the behavior or the general shape of this function. And of course, we can check our work. This time I'm going to use Desmos. So I've entered the equation exactly as it was given to us on our worksheet. And here's the picture. I'm going to adjust the scaling just a little bit. And this is the nice thing about Desmos, is that you can pinch to zoom pretty easily on a touchscreen device. And wouldn't you know it, I think the behaviors that we predicted are indeed what we see in this particular graph. The left side tail is pointing down. The right side tail is pointing up. We bumped into the x-axis and turned away at -3. We bumped into the x-axis and turned away at +1/2. In fact, I can tap on the screen to see that. And then finally, we crossed through the x-axis at +2. These other gray marks indicate important components on the graph, and if I zoom into this gray mark in the center, that should be our x-intercept. I'm sorry, our y-intercept, which is indeed located at -5.625, as we predicted. So this type of analysis is important for a college algebra student to be able to execute, because recognizing the behavior of functions without actually executing the functions or relying on a graph is very important, especially when you move on to your calculus class next year. To finish this video, I would like for you to complete these two examples. In each case, I'd like for you to rewrite the function in standard form. That means to expand and multiply and distribute. You should be able to find all x-intercepts and y-intercepts. The y-intercept is your constant of the polynomial, and your x-intercept are the zeros. You can find those in factored form. Identify the multiplicity of each zero and make a note of that. And with the multiplicity of each zero, sketch a graph of the function. You can skip this for the time being, and we will cover it in another video. But go ahead and pause the video now and try your hand at these two examples. You can resume playback in a moment to check your work. In example 1, I distributed the 3 into the first group first and simultaneously expanded this exponent. In the second step, I FOILed those two terms together and then distributed the 3x and the -21 into this term and combined all like terms. The x-intercepts were easy to identify in factored form, +7 and -3. The y-intercept, well, we could have done the math as I've shown here, because y-intercepts occur when x is equal to 0, or we could recognize that the y-intercept is indeed just the constant at the end of the polynomial. At the 0, or x-intercept of 7, 0, the point 70, we had a multiplicity of 1, so the graph will behave linearly at that point. At -3, 0, we have a multiplicity of 2, so the graph will essentially behave like a quadratic. So with that in mind, and our understanding of polynomial end behavior, we have a positive leading coefficient and an odd degree. The right tail was pointing up, the left tail was pointing down. At a multiplicity of 2, we had to bump into this 0 and turn away. And with a multiplicity of 1, we had to strike this 0 and continue straight on through. I feel that this would be an accurate representation of the graph. And in addition to the multiplicity, I forgot to mention that, well, we've got a y-intercept of -189, which indeed could be down here, a negative value based on the y scale. Similarly, we went through the same work, or I went through the same work on this example here. I noted that the exponent was 1. It was hidden, not written in either of these cases. So right off the bat, this x squared, this first power, and this first power, when multiplied together, should have produced x to the 4th, which we did obtain after distributing and combining all like terms. X-intercepts, therefore, are located at 0, +2, and -3. The y-intercept itself is 0, because when x is 0, y is 0, as well as there's no there's no constant at the end of this expression. And so at this first 0, 0, 0, we had a multiplicity of 2, and at the other zeros, we had a multiplicity of 1. So the function behaved linearly at these two zeros, at negative 3 and positive 2. But at 0, it behaved more or less like a parabola, with a positive leading coefficient and an even degree this time. The right side tail is pointing up, and the left side tail is also pointing up. The graph will run through this intercept at negative 3, and it runs through this intercept at positive 2. And therefore, to make a smooth and continuous line, the graph would have to bump into the 0 here at 0, 0. And this sketch does support the notion that our y-intercept was 0 as well. Recognize there's a lot of interpretation going on with these types of questions, so please, if you have questions or any concerns about how this was completed, reach out to me and I'll try my best to further clarify. Thanks for watching.